Alright, in this unit we're going to be looking at conics on the complex plane. Now the conics we'll be learning about are lines, circles, ellipse and hyperbola. Now on the complex plane we're also going to be looking at the regions that they can form depending on the type of complex equation that we've got. We'll begin with looking at lines and circles, but before we do we need to understand a little bit about I'll remind you about some basics here from that you already probably know. If we had a number line here, here's a number line and we've got two numbers on the number line, say a 10 and a -10, and here's 2, for example. If I was to ask you what is the distance between these 2 points, what is the distance between those 2 points, you'd probably very quickly tell me that it's 8, because you just go 10 minus 2. Okay, so I'll just write that down. We've actually gone 10 minus 2 is equal to the distance between those 2 points. If I ask you for the distance between these 2 points, between point 2 and point -10, here's 0 somewhere, you'll very quickly be able to tell me that that distance is 12. How did we get it? You could have gone 2, take away -10, and we would get 12. What if we went, here's another point here, this is -15. The distance between these 2 points you can quickly see is 5. What if we went -15, take away -10, then we would get -5. So if we were actually looking for the distance between 2 points, we could say, well, we know the distance is not -5, we could take the absolute value of that. Absolute value of that will give us 5. So the clear point that you need to understand here is that to find a distance between 2 points, we subtract 1 point from the other. On the complex plane, if we wanted to find the distance between these 2 points, we might call this Z1 and we might call this Z2. So now we're being much more general rather than using specific points. If these 2 points are on the complex plane, the distance between those 2 points would be Z1 take away Z2, or you could do it the other way around. But knowing that we could get a negative answer there, we take the absolute value of that. So Z1 minus Z2 is the distance between Z1 and Z2. That is a really important point that you need to understand as we go into looking at conics on the complex plane. Z1 minus Z2 is the distance between Z1 and Z2. Alright, let's look at let's get a bit more specific and let's look at lines. You may remember from our previous study of lines when we were looking at the Cartesian plane, we actually looked at this definition of lines previously. But on the complex plane, a line is a locus of a point Z that moves in such a way so that it is always equidistant from 2 fixed points, Z1 and Z2. So very quickly we could draw a bit of a diagram of that. Here's 2 fixed points, Z1, Z2. They don't move. Now Z is a movable point. It's our point anywhere on the line and it has to be equidistant from Z1 and Z2. So the obvious place for that, as we've looked at before, would be right smack in the middle between those two. It also could be out here and it could be anywhere along this line. Z could be here where that distance and that distance are equal. or Z could be down here where that distance and that distance are equal. So Z could be anywhere along this line so that it is equidistant from Z1 and Z2. How would we write this in complex form? Well, remember, what we're really saying is that this distance equals this distance. So back on this previous page, we knew that the distance between 2 points was just one point minus the other point. So on this example, this is a movable point Z. So this distance here is going to be Z minus Z1, absolute value. This distance here is going to be Z minus Z2, absolute value. And according to our definition of the line, Z1 minus Z2, sorry, Z minus Z1 I should have written. Z minus Z1, that distance, must be equal to Z minus Z2, that distance. And this is the standard form of a circle, the standard form of a line in complex form. So standard form of a line. Z minus Z1 equals Z minus Z2. We'll now move on to looking at the equation of a circle. After that, we'll look at how to actually use these things. So let's move on to the equation of a circle now. And I have here the definition of a circle, and we've seen this previously as well with our Cartesian form. On the complex plane, a circle is the locus of a point Z which moves so that it is always equidistant r from a fixed point Z1. Is always equidistant r from a fixed point Z1. So here's our fixed point Z1. And we all know what a circle is, and we know what Z1 is going to be. Z1 is going to be the center of the circle, and Z can be moving anywhere around here. My diagram's not real crash hot. Z can be anywhere around here so that it is always equidistant. That distance will be the same all the way around. We know for a circle that's called the radius. We'll call it r. So this distance here we know is Z minus Z1 magnitude or absolute value. So the standard form of a circle, I can't spell. The standard form of a circle is Z minus Z1 magnitude. In other words, this distance is always equal to a constant r. So there we have the standard form of a line and the standard form of a circle. In the next video, I will show you how we can convert between the complex form and the Cartesian form, and also how we could possibly go about sketching some of these graphs.